Welcome to a course on complex analysis. In this lecture, we are going to talk more about analytic functions. In the previous lecture, we have seen the equivalent form of a Cauchy-Riemann equations and we have introduced the concept of analytic functions. But still, there are many more to explore in the concept of analytic functions, and that is what we are going to do in this lecture. In the previous lecture, we have seen the definition of an analytic function and the entire function, and we have seen some examples where the function fails to be analytic at only one point and the function which is analytic at no points in the entire plane. Okay, we have seen these things. Now we would like to make some note. Okay, so the note tells us that and necessary but by no means of sufficient. That is, a necessary condition for a function to be analytic is that the function is continuous throughout the domain. Okay, if the function is continuous throughout the domain, then the derivative of course exists and it satisfies the analyticity as well. So the thing is that a necessary but not sufficient condition for analytic function is f is continuous throughout D. Okay, it by this they mean to say that the analytic function is continuous throughout the entire domain. If the function fails to be continuous at some point in a domain, then of course the analyticity would never happen. Okay, so sufficient conditions are obtained through differentiation formulas. Okay, algebra of analytic functions is also analytic. So by algebra I mean the sum, difference, product and the quotient. Okay, those things. And so this is the first note and this is the next note, and composition of analytic functions is also analytic. So here we are not going to prove any of these things, so we just see these things are happening to be true. Next we are going to see a property in the form of a theorem. So let me state the theorem first. If f prime evaluated at z is 0 everywhere in a domain D, then f of z must be constant throughout D. So if the derivative of a function is 0 everywhere in the given domain D, then the function is of course a constant. That is evident from the course on real analysis, but how is it happening in complex? That is what we are going to see now. So let us take our f of z to be u of xy plus iota times of v of xy. Okay, so let us make our assumption that f prime evaluated at z is 0 in the given domain D. So f prime of z takes the form ux plus iota times of vx by sufficient condition of differentiability. Sufficient condition of differentiability. Right? So by our assumption we get ux plus iota times of vx is 0. So this is one way. This is one thing. Equating real and imaginary terms, we get ux is 0 and vx is 0. So let us mark this as equation 1. Next we observe that by Cauchy-Riemann equations and equation 1 gives vy minus iota times of uy is 0. Again equating real and imaginary parts, we get vy is 0 and uy is 0. Okay, therefore what we conclude is ux uy is 0 and vx vy is also 0 at each point in D. So with which we need to claim first what we are going to prove is that u of xy is constant along any line segment L extending from a point P to a point P prime and lying entirely in D. So whatever we have said, okay, this is what we are going to prove. That let me give you here. Okay, suppose if this is your domain, okay, so if this is your domain, you have you have two different points P and B prime. Okay, you have a line segment that joins these two lines. Okay, so sorry for it. So we must have a line segment and line segment between P and P prime, these 2 points. This line segment is taken as L. Okay, so we'll have to prove along this line segment this function is constant. Okay, ux is 0, uy is 0, vx is 0 and vy is 0. This means that your function u behaves as a constant along x-axis and your function u behaves as a constant along y-axis. Since there are no changes in the x direction and y direction, we can come to a conclusion that in that direction the function is constant. Okay, but that does not guarantee us that the function is constant throughout the domain. That is why we are choosing some arbitrary line segment and we are going to prove along that line segment the function is constant. Whatever we are doing for u shall be done for v as well. So we will do only for the function u and that shall be extended to the function v. Right? So having considered these things, we move further. Now let S denote the distance along L from the point, and big U denote the unit vector. So actually this big U is a vector. So unit vector along L in the direction of increasing S. So what they have said, if we do it in the graph, suppose if in this direction itself, so in the direction we will have a unit vector U, and the measurement is the distance is S. So once we denote these things, we shall write the derivative of U, any function U with respect to S is gradient of the unit vector in the direction, the gradient of the function that we take and dot product with the U vector. So here the grade U means Ux I vector plus Uj J vector. So the complex function is now treated as a function, the things happening in R2. That is why we have written these vector notations. Let us mark this equation as 1 and this equation as 2. We deduced Ux and Uy is 0 everywhere in D. Thus grad U is 0. Hence du upon ds is 0. So with which what we conclude is that U is constant along L. Now we have proved this is happening to be true for the line segment that joins P and P prime. Now if you take another point Q and join these two things, now you can take this point as Q and see these things are happening. Now you can prove the same thing happens to be true in the line segment P prime Q. Like this you can prove for any line segment. So with which what we conclude is that inside the domain D we can have only a finite number of line segments. Therefore, the function U of xy is some constant on D. Similarly, we can prove for the function V that happens to be some constant on D. Therefore, f of z, that is u of xy plus iota times of v of xy, is a plus iota times of beta, which is some complex constant on the domain D, and this completes the proof. So now what we are going to do is that we are going to see some examples. So the first example that we consider is f of z is z cube plus 4 upon z, sorry, z squared minus 3 multiplied with z squared plus 1. Okay, so this function is analytic in z plane except for the singular points z equals plus or minus under root 3 and z equals plus or minus I. At these 4 points the function fails to be analytic, but in all other points the function is analytic. Okay, so the next example, f of z is hyperbolic cos x cos y plus iota times of hyperbolic sin x sin y. So if you write this as a componentized function, your u of xy is hyperbolic cos x cos y and v of xy is hyperbolic sin x sin y. If you differentiate with respect to x, you would get hyperbolic sin x cos y, and if you differentiate this one with respect to y, then you would get minus hyperbolic cos x sin y. And similarly here it is vx is hyperbolic cos x sin y, and this is gonna be vy is sin hyperbolic sin x and cos y. So we observe that ux is same as that of vy and uy is same as that of minus vx. Okay, here we have not imposed any restrictions. Here no restrictions are imposed on x and y. Thus the function, given function, is an entire function. Sometimes there may be a situation where your function will satisfy your CR equation, and that will happen to be true only when you impose some conditions on x and y. Here that did not happen. That is why it is an entire function. Right? So the next problem, suppose f of z, that is u of xy plus iota times of v of xy and its conjugate f prime of z, okay, sorry, f of z whole bar, that is u of xy minus iota times of v of xy are both analytic in D. Okay, by analyticity of f of z, we have, if the function is analytic, it means the function is differentiable. If it is differentiable, then it will satisfy Cauchy-Riemann equations. Okay, in the previous problem also, using Cauchy-Riemann equations, we have concluded that the function is analytic everywhere on the entire plane. Here this satisfies your Cauchy-Riemann equations. Okay, CR equations are satisfied and all these four quantities exist and continuous as well. So by the necessary and sufficient condition, we come to a conclusion that the function is differentiable. And the function is differentiable everywhere on the z plane. That is why we have come to the conclusion that the function is an entire function. Here, using, okay, now coming back to the third problem, because of the analyticity, what we have is ux is vy and vx is minus uy. Okay, now using analyticity of f of z bar. Okay, so before looking into the analyticity of this function, let me write this function as big U of xy plus iota times of big V of xy. Okay, what is your big U? That is simply small u, and big V is minus small v. Okay, now using its analyticity, what we are going to have is that your big Ux is big Vy and big Vs x is minus big Uy. Okay, your big Ux is simply Ux, big Uy is simply Uy, big Vx is minus small vx, and big Vy is minus small vy. Okay, now we'll have to substitute the values of big ux, uy, vx and vy into this. So let us do it. So big ux was simply small ux. Okay, so ux equals what? Big vy. Big vy is minus small vy, and big uy value is small uy itself minus times of, and big Vx is minus Vx. So this becomes simply Vx. Okay. So let us mark this as equation 2 and mark these set as equation 1. So whatever we have is reversed here. Okay. So by 1 and 2 we conclude ux has to be equal to 0 and uy has to be equal to 0 and vx has to be equal to 0 and vy has to be equal to 0, just because ux is equivalent to vy as well as to minus vy. This is possible only when your ux is 0. Okay, so when ux is 0, that trivially tells us that vy is also 0. Similarly, we can prove uy and vx are also 0. Okay, when we get these things, thus f prime of z is ux plus iota times of vx, which is 0, plus iota times of 0, which is 0. Okay, by the previous theorem we can conclude that f of z is constant throughout the domain D. The next problem that we are going to see is, we are going to consider a function f which is analytic throughout a domain D. So this is the domain in which we are considering a function f which is analytic. Then assume absolute of f of z is constant throughout D. Okay, so given that it is constant, we know that this is some real value, so we shall write absolute of f of z is equal to c for all z in D. Okay, where c is a real constant. Okay, we know that it is some real constant, it cannot be negative too. Suppose c is 0, then your f of z is 0 everywhere in D. Okay, this is gonna happen. Now suppose c is non-zero, then what happens? We shall write f of z as f of so then your absolute of f of z whole squared is c squared, and this may be written as f of z bar equals c squared. Hence your f of z may be written as c squared upon f of z for all z in D. Okay, now using the property, if a function is analytic, like or I may write by the algebra of analytic functions, c squared, which is a constant that is an analytic function, upon f of c, which is also assumed to be analytic. So this quotient is analytic. This implies your f of z bar is analytic. Thus f of z and f of z bar are analytic. By the previous problem, there what did we do? We have assumed the function is analytic and the conjugate is also analytic. This is what the assumption that we made, and with the help of these assumptions we proved such functions are constant. Okay, so if these two are analytic, this forces that f of z is constant throughout D. Here we consider two cases, that is when c is non-zero, what is happening, and c is 0, what is happening. When c is 0, you get your function to be 0, which is also a constant, right? If the function if c value is non-zero, then you are getting your function value is some constant throughout the given domain D. And this completes the problem. In the upcoming lecture, we are going to talk about harmonic functions, which are parts of analytic functions. Let us explore them in the next lecture. Thank you.